thanks the organizer for giving me this opportunity. So I'm going to talk about Khintchine's inequality for graph-independent semicircles. So there are a bunch of words. I'll explain each of these hopefully. Okay, so hopefully by the end of this talk, each one of these words will make sense, what it means, and I'll state my result. But I want to basically take this opportunity to kind of provide a broad overview of this whole field. So I'll talk mostly about what is called the strong convergence phenomena, and I'll try to motivate how this work kind of sits in between a large body of work and why it's important. So it's more like a semi-philosophical talk where I'm going to advertise a lot of work and this field to this audience. So there is some graph here, and the graphones will make some appearance, but it's really not a random network thing. So sorry about that. So let's start with the Khintchine's inequality, or what I'll often call classical Khintchine's inequality. This is due to Khintchine from 1923, I believe. So the statement is as follows: you take Rademacher random variables, IID Rademachers. So let's say you have collection of IID random variables and probability that Ri is equal to plus minus 1. And for such random variables, we look at the sum of these or some linear combinations, and we are interested in estimating its LP norm. When I say LP norm, what I mean is that you look at the pth moment and then you take the 1 over pth rule. So I'll sometimes write expectation and sometimes I'll just use this norm. It is just the LP norm in your suitable probability. And the goal is to understand this quantity in terms of the L2 norm of this quantity. And what Khintchine essentially proved is that this is less than or equal to some constant times the L2 norm of the same quantity, which, right? And in fact, there is a matching lower bound. So there are some constants A, P, and B sub P that depends on P, but what is important is that it does not actually depend on N. So this is independent of N. There is an absolute constant that depends only on P, such that the LP norm and the L2 norm are comparable. Khintchine's motivation was to study basically what are called the random series. At that point of time, people were basically studying almost sure convergence of random functions and so on, and it got used there. But there is a nice operator theoretic viewpoint of what this is basically saying. So what this is really saying is that if you look at, let's say, the span of these Rademacher random variables, you can even take an infinite collection, doesn't matter, and you look at its LP closure, then this is isomorphic to the span of this, and you take the L2 closure. Okay. So notice this side is a Hilbert space. We all love this object. What we are saying is that this Banach space is actually linearly isomorphic to this Hilbert space. And this is a big deal for operator theorists, that these two spaces are isomorphic. But operator theorists care about something a little more than this. So this is an isomorphism between these two spaces. But operator theorists will care about something called a complete isomorphism. So for those of you who know, what it means is that the operator space structure on these spaces might still be different even if they are isomorphic. So you want the operator space structure to be the same. But in more down to earth term, what it actually means is the following: that you want to replace these coefficients AI, which are scalars here, by matrices, or more generally operators on the Hilbert space, and you ask, is an inequality of this form is still true? If that is the case, then you will say that these spaces are actually completely isomorphic. In other words, in other way to think about this is that if you have a matrix of these Rademacher random variables, are their norms still comparable? Their Schatten p norm and their 2 norm, are they comparable? So what one would be interested in is really understanding the norm of objects like this. So Ri's are my Rademachers. And let me write P. I should write more precisely as P. So this is Schatten P norm, or you can, on a finite dimensional spaces, it doesn't matter. You can put any norm that you want. But we would like to be able to compare this with the L2 norm of this. Okay. And obviously, there should be something here. I'll come to this. I should maybe mention one other important thing here is that this quantity, you can kind of imagine from the central limit theorem that B sub P should grow at least like square root P. It cannot be too small. I mean, if you really divide this by 1 over square root n, then you can morally believe that this is actually like a Gaussian. So you are comparing really the pth moment of a Gaussian with the second moment of the Gaussian. So it must scale like at least a square root. And this was actually an important problem again, finding this exact constant that actually makes this inequality work. And it has important consequences in metric geometry, for example, the projection of L1 balls or L2 balls, for example, on some hyperplane. If you want to control the volume, then you will actually need this exact constant. So, okay, we are interested in some quantity like this, or people have been interested in quantities like this. So, and once again, we will have some matching lower bound, but throughout the talk, I'll often ignore the lower bounds. They are usually not that difficult to prove. The main part is to actually prove this upper bound, that you can bound the pth norm with, Okay, so this brings us to something called non-commutative Khintchine inequality. And let me make a small change. Instead of Rademachers, I mean, you can do it with the Rademachers, but what is probably more familiar to the people is if instead of Rademachers, let's say you have Gaussians. So you have IID Gaussians. You take these deterministic matrices A sub I, and you look at their linear combination. This is a very, very general class of random matrices, actually, in the sense that any matrix with the jointly Gaussian entry, you can actually write as the sum of independent Gaussians with some deterministic matrix. So if you can actually understand the norm of this matrix, then you are basically saying that you understand the norm of a large class of random matrices, basically any random matrix which has jointly Gaussian in. So we want to understand this quantity. And this was done by Lust Picard and PGA in a series of paper. And this is, I think, from 93, 94. These dates are approximate. This might be off by a few years, but around this time. What they basically showed is that that such an inequality holds. So basically, non-commutative Khintchine inequality holds. You have, and once again, you can prove it for a very general class of random variables here. Essentially, anything sub-Gaussian sort of works. So this precise constant that you get here, that will depend on which random variable you are working with. But if you are only care about the existence of some constant depending only on P, then you can do it in a pretty general setup. So let me write this P now. This is less than some constant. Okay. Now this, for example, I'll write it in a little more familiar form to at least to the people in the random matrix theory community. This was used by Rudelson to give a proof of a result of Bogen. And what he basically showed is the following. So these are for the Saturn P norm. We are working with the matrices, but you can ask the same question about, yes. Yeah, so AI has dimension, let's say D. So AI is our, let's say, D by D. And for the purposes of this talk, maybe I'll also assume, let's say they are symmetric. It doesn't really matter. It will just simplify some of the expressions that I'm going to write. Yes, throughout this discussion, D is fixed. This one. No, so this one doesn't depend on D in this expression, but the next what I'm going to write, if you care about, let's say, the operator norm, which you should really think of as P is equal to infinity, then the dimension will play a role. And this is what basically Rudelson did. PG's book on operator theory, it has a passing line which says that the proof in the Rudelson's paper that was suggested by Gilles Pizier, although Rudelson's paper doesn't make any mention of it. So I don't know who this proof really belongs to, but this is the result that the operator norm of this, once again, this is in expectation. This you can bound by the square root log of D times the expectation norm. Okay. And let me actually write this one as well, a little more find this. Operator. So this is something that you get, and you can actually get it from here. We actually know this constant precisely, and what happens is that in order to bound the optimal operator norm, you take P to be something like log in the dimension, and that's where basically this quantity falls. Okay. But now there is a dependence in the dimension. Okay. Now, interesting, as I said, for example, that if you replace these. Yes. So there is also an expectation, and this is basically if you just do the expectation of this L2 norm, if you put the squares and you take the expectation, then this is what you will do. Yeah. Yes.
So you first take the norm and then you take the expectation? And what's the exact definition? Like trace of.
This is the pth power of the Schatten P norm. You take the expectation and then you take the 1 over pth root.
Okay.
Okay. Now, how good is this bound? For example, this bound is very good and not so good in two different ways. So if you take, for example, these AIs to be matrices that commute, okay, and keep in mind that RIs, if you take them to be Gaussians, it's probably much easier to intuit about the Gaussian. So you can basically diagonalize all of them simultaneously, let's say. And if all of them can be diagonalized simultaneously, then the operator norm will be basically the maximum of the diagonal entries. And on the diagonals, what you are basically getting is the sum of IID Gaussian. So you basically have Gaussian random variables, D many of them, and you are looking at their maximum. So you expect this log of D kind of a term to appear, square root of it. You are basically looking at the maximum of D Gaussian if all of these things commute. So let me write this, that if AIs commute, then this square root log D penalty is optimal. On the other hand, there is a different regime. As I said, for example, if you take RIs to be Gaussian, then you can actually write, yes.
Just repeat what you said a minute back. So D log D comes from sum of maximum of D many.
Maximum of D Gaussians.
Yeah. Okay, so there are D Gaussians on the diagonal?
Diagonals, yes.
Oh, okay, thank you.
Under the regime, if you, as I said, for example, this is very expressive. It can represent any Gaussian matrix in some sense. So if you take the Wigner Gaussian matrix here, so I call this X. In that case, the norm of X, greater norm, this we basically know is like 2 times this quantity that I'll call maybe sigma of X. I'm calling this sigma of X because as I mentioned, this is, I'm thinking of this as some kind of a standard deviation. If you write your matrix X, then this is the expectation of X square, and then you are taking the square root. So this is sigma of X, just for the notation, simplify my life. So the point is that you don't have to pay this logarithmic price here. Okay? To summarize, if all these AIs, these coefficients, they commute, then log D you cannot avoid, you have to pay that price. But in the generic cases, the log D is actually very loose and you don't need to pay this price. Now, this logarithmic dependence, although seems very mild, this exact problem where you have to actually control the operator norm of the sum of these IID Gaussian matrices, this appears in many different problems. Pravesh Kothari has a nice lecture notes where you can actually read a lot of applications. So it appears, for example, in the graph sparsification, even in, for example, neural networks, you see more general polynomials of IID Gaussian random matrices, and you will have to control their norms. And this square root log of dimension, this becomes a huge penalty to actually pay. So people are interested in understanding, do we really need to pay this price or not? And what I'm saying is that if AIs are commuting, then you need to pay this price. But if they don't commute, then you don't actually need to pay them this price. So the slogan is that non-commutativity helps. What I mean by this is that the more non-commutativity is there in your system, this norm should be much closer to this. One way to make this idea precise is to realize that I'm going to now define an object, and I'll define this more precisely after a few minutes. But here, for example, all the non-commutativity is coming from this matrices, but there is a way to introduce non-commutativity in the system at the level of random variables itself. So instead of Gaussians and Rademachers, we can actually put non-commutative random variables in some sense, whatever that means. So I'll define those things much more precisely. But for the time being, just trust me that there are these objects that we will call semicircles. And these are free semicircles. So I'll define what those objects are, but they are really some operators on some Hilbert spaces, and they will come in the free probability. But you should really think of this as a proxy. And what we know in this case is that the norm of this is actually comparable. So there is some constant price. It can be slightly bigger than 2, but let me just write 2 times the sigma of X, by which I mean basically this quantity. Okay. Why is it important? It's important because what this is saying is that the moment you have non-commutativity in your system, although here the non-commutativity is coming from these coefficients, so we sometimes call this intrinsic freeness. The system has some kind of an, this is intrinsic freeness. Here we are putting this non-commutativity or this freeness by these random variables, so we will call this extrinsic freeness. But the idea is that if you have enough of this intrinsic freeness in your system, then the norm should behave like this free system. So this leads us to the next step, that what we would like to do essentially is to make a statement, a rigorous statement that actually captures this phenomena, that can this system be compared directly to this X of free? Okay. So this question was raised and first analyzed by Trop, I think in 2019. And then there is a series of work by Trop, Raymond van Handel, and Afonso Bandera. And there are a lot of people involved doing this. So what Trop suggested is to basically prove an inequality of this form, that can we actually bound the operator norm of X. This is my X, the same X that we have written here, by something that depends on the sigma X. You can pay some small constant price here, doesn't matter, but we want this price to be independent of the dimension, plus something which we do not know what this is, and maybe you have to pay some logarithmic price in the dimension. So an inequality of this form, where this quantity should somehow be a measure of non-commutativity in your system. Okay? Or in other words, it should measure the freeness in your system, intrinsic freeness in your system. Okay? And Trop actually proved something like this for a class of random matrices. Okay? And now we have much more precise, for example, concentration estimates, which essentially tell you that not just after taking the expectation, if you just look at the operator norm of this random matrix and you compare how far it is from the operator norm of this quantity, which is, by the way, a deterministic quantity, then you can bound it. What is the deviation? So there are good deviation results. You have seen some of this, for example, in the yesterday's poster session. Bodhisattva and Vishak, they presented something along these lines. So I mean, they used the concentration estimates like these. So now, there are two kind of body of work here that one can do. There is a lot to do here, but one of the things that one can do is that you take this random matrices, some random matrix ensembles X, and you would try to prove a statement of this nature or something like this in probability, which basically says that you can compare the operator norm of this and now we have developed some tools, namely something like polynomial methods and so on, which allow you to prove results of this kind. But this is akin to, for example, concentration inequality. You basically prove that there is some quantity and it is concentrated around its mean and its median or whatever. But then the next order of business is to actually understand what this object really is. Okay? So there are tools that allow you to basically localize this quantity near this quantity, but then you need a different tool to actually understand what this quantity is numerically. Okay? And this is where a Khintchine inequality kind of a statement comes up, because we will basically try to do this kind of a thing, but we will replace these Rademacher random variables by these more general free random variables or semicircles. And then the Khintchine inequality will provide a good estimate on its Pth norm or its operator norm. Okay? So that's what the goal of this talk is. So that is kind of the motivational speech for why this work is somewhat relevant. And now I'll just make some definitions. Yes.
In this general bound, what could be the beta? Like there, for example, the beta is equal to half k-min due to the IID-ness of the Gaussians, the maximum of Gaussians.
Yes.
But it could be something else also. You're saying that if you take general entries.
Yes. So the first bound that Trop proved was very bad. It was something like log d to the power 3/2. But the whole point of that estimate was not to provide the best estimate, but rather to say that the contribution coming from the non-commutativity can be separated. And therefore, if your system is non-commutative, then this will also decay. And this quantity will not really matter. But since then, it has been refined, and there are many different bounds.
Okay, just to be precise, like make my question precise. Does this error always come from maximum of some IID variables, or this bound here?
This term,
yeah.
At least in the existing one or two proofs that I have seen, yes, in those cases. So now let me give you a crash course in pre-probability. So we all work with the random variables. Our random variables live in some nice algebras. For example, they have finite moments or they are bounded, so they live in L infinity of some space and so on. What free probability does is that the setup is that you start with some von Neumann algebra. So A will be some von Neumann algebra or some C star algebra, and tau will be a trace. So this is a linear functional from A to, let me write R. You can take the complex numbers. We want this algebra to actually have the identity, and the identity should get mapped to 1. Okay, and we need a bunch of other properties. Basically, this should be positive. What I mean by positive is that it should send positive elements to positive element. And how do you define positive elements in an algebra? Well, elements of this form, A times A star. Okay. We also want it to be faithful, which essentially means that this doesn't vanish if your element is non-zero. Now, what can we do with this setup is that an element in this algebra is what we will call a variable or a random variable. There is no randomness here. It's just an element in the algebra. But these traces kind of allow you to compute the moment of these variables. So you can define, for example, these objects. These will give you some number, and you can think of it as the pth moment of this variable A. Right? So for the purposes of this talk, I'll always take these A to be self-adjoint. Otherwise, you can also compute the star moments and so on. So you compute the moments of A, its adjoint, and all their products and so on. To simplify my life, everything will be self-adjoint. So these will give you moments. And turns out that with this moment sequence, you can associate a measure. So if you write these numbers, m sub p, for every power p, then there is a measure which has precisely this as the moment. Okay? So there exists a measure. Yeah. In this sense, we can say that mu is the law of this variable A. Okay? So its relation, when we say that mu is the law of A, there is really no randomness. It's just that you have a moment sequence, and you have a unique measure that. And this is actually a probability measure. If you just put p is equal to 0, you can see that the total mass has to be 1. So this is a bona fide probability measure that you actually get out of it. So now, yeah.
So it's a C star probability space, right? I mean, the measure is compactly supported or something like that? Or?
Yes, yeah, that's a very good point. That the elements in my algebra, since they have finite norm, what you can basically see is that this measure will have bounded support. So in some sense, this setup is a bit restricted. It only cares about the bounded random variable, so to say. There is a way to extend this by the affiliated operators and so on. I'll not go into that. So all my random variables that I work with, they will be bounded random variables. Okay, so semicircles. These are again some objects in some C star algebra, and they should have the right moment in the sense that S is semicircular. If the moment, this agrees with the moment of the semicircular measure. Okay, this is our famous semicircular measure with the density proportional to this. Okay. So this is a probability measure, which is very common in the random matrix theory literature at the least. So there are random variables, or there are variables in some operator algebra or in some von Neumann C star algebra where such objects exist. What is more important is that in the classical probability, we have this notion of independence, which in some sense tells you that if let's say X and Y are independent, then the expectation of any polynomial of X times any polynomial of Y. Let's also pretend that the P of X and P of Y, they have mean 0. Then this splits. So this is classical independence. You want to do it for, let's say, all functions, but we just start with, let's say, polynomials. We want to define freeness using a similar method, but it turns out to be something surprisingly different. So you have S1, S2, let's say Sn. For me, they will be just semicircular random variables, but you can take them to be anything in your C-star algebra. And we say that they are free if, and we also, let's say, assume that their traces are equal to 0. So what we want is that trace of Si1, Si2, Sik, this should be equal to 0. Whenever I1 is not equal to I2, not equal to I3. Okay. Now this is a truly non-commutative phenomena for this region. That suppose, for example, what this is saying is that if you take S1, S2, S1, S2, the trace of this quantity should vanish. But if S1 and S2 could actually commute, then you can actually write it as the trace of S1 square times S2 square, and that will vanish only when S1 and S2 both actually vanish. So this phenomena you cannot really replicate with the commuting things unless you are actually looking at degenerate commuting. Okay? So this is a truly non-commutative phenomena. You cannot quite get free objects which are commuting as well as free unless they are trivial. So these kinds of phenomena, they happen only when you go to the infinite dimensional operator spaces and so on. So matrices to a certain degree can replicate some phenomena like this. You will not get exactly the trace 0, but something close to 0 and so on. That's why they are useful. So this is the notion of freeness. And now let me define very quickly what I mean by G independence. And this one I'll not define very properly. But this is a notion of independence. So we now know two notions of independence: classical independence and freeness, free independence. What we want to do is that we want to consider mixtures of these. So for example, I'll just give an example. Imagine that you have a scenario S1, S2, S3, and you have a graph and 3 vertices. Okay. So you want these 3 semicircular variables, which means you want some algebra, you want some element there. They should have these right moments, but you also want S1 and S2 to be independent in the classical sense. So they should really be independent random variables. You also want S2 and S3 to be independent, but you also want S1 and S3 to be free. You can see the pattern. What I'm basically demanding is that you are given a graph, and every vertex of the graph encodes a variable, semicircular variable. And if there is an edge between a pair of variables, then you want them to be independent in the classical sense. If there is no edge between them, then you want them to be free. It's by no means obvious that such a thing should exist. Okay, but such a things exist. That's why we are talking about this. So this was done by Lotowski. There might be an additional O somewhere. And then it was kind of again revived by Ronald Speicher and so on. So such an object exists. You can actually cook up a G-independent collection of objects for any given graph G. Now, last point that I should mention about this is that if you take your graph G to be an edgeless graph, then what you are basically asking is that n semicircular random variables that are free. So you are actually working with the free collection of things. If you take G to be a complete graph on n vertices, then you have edges everywhere. So you are basically looking at the collection of independent semicircular random variables. So this, yes. Yes.
Pairwise concept.
Here I'm just defining this as in this way, just to give you the intuition that this is one way to think about this, and this is precisely the reason why one has to show the existence of such objects. Because if you want to understand their joint moment distribution, then you need to understand their joint behavior, and that is not fully captured by just saying that pairwise things are dependent or free. So that's why there is a non-trivial amount of work, but intuitively the way you should think about this is that there is an edge, so they are independent. If there is no edge, they are free. So this graph independence kind of captures this whole story of independent random variables and free random variables. And then we can ask the following question, that if I give you a bunch of random variables and a graph Gn, and these are, let's say, Gn independent. So just let's say G independent. And I now look at this object. So now notice this. This is important. You cannot really multiply these SIs. May potentially live in some C star algebra, so I really need to take their product. But I can make this linear combination, and I'm looking at their LP norm, which again you have to be a bit careful. There are these two components in the tensor, so I'm actually looking at the Schatten P norm on the first component, and I'm looking at the pth moment or the trace applied on here. Okay? So there is a norm here that I'm just going to say P, and the goal is to basically say that this is bounded by the L2 norm So this one, again, we can write completely explicitly in terms of these AIs. And in fact, it turns out to be exactly the same quantity that you have already seen there. This is literally just this. I'm assuming symmetry. If there is no symmetry, then instead of AI square, you will have AI star. But then you will also have to look at AI star and AI take their maximum and so on. And then you pay some price here. So there is a quantity that depends on P. So there is something that depends on P that is fairly explicit. We can write it in terms of the Catalan number. And then you should see some parameter that actually depends on the graph G. Because in this free setup, what you already saw is that you should actually not pay any price, and your dependence on P should actually be just a constant. While in the IID case, this should actually grow like a square root P. So the graph actually plays a role. But the question is which parameter or which quantity of the graph actually controls this norm? And the answer to that is the clique number. So omega of G, which is the largest complete graph that you have inside your graph. Okay, so this is the clique number. There is a matching lower bound. I'll not write. So this is basically the theorem, and this is joint work with a friend, Patrick or Santos and Pierre Yusuf. Okay, so this is the final object, and this recovers the Khintchine's inequality in the IID setup. I'm writing the result for the Rademacher's, but you can write it for more general random variables. So if you just do it for the graph G, which is the complete graph, then you will actually recover something like this. And if you do it for the free random variables, then you will recover a result of Lust, Picard, and Pizier, who actually proved the non-commutative Khintchine's inequality for these semicircular random variables. And in between, it basically interpolates. It interpolates the whole regime. So that's one thing. And let me make one final remark that around the same time, basically, this was also proved by another group, basically Benoit Collins and Akihiro Miyagawa. they proved this where instead of this omega g, they had square root of lambda 1 plus 1. So this lambda 1 is the largest eigenvalue. So sorry, this should also be square root of the clique number. So what I should basically say is that this bound is actually sharp. We know that you cannot actually improve on the clique number. There are examples where you actually match the clique number. And the clique number can be significantly better in practice. For example, for a typical graph, by which I mean if you take an Eratosthenes graph, then the largest eigenvalue will be of the order n times p, while the clique number is typically of the order log of n. So you actually get a significant gap between the two. So this is kind of the result that I wanted to say. Thank you very much. If you have any questions.
Thanks. Question.
Right? Dependence of D in the right-hand side there.
So there is no dependence on D that you see right now because I'm looking at this P norm, but you can do this with the L infinity norm or operator norm. If you do that, you will see the dependence on the D. The dependence on D basically comes from choosing a suitable P with which you can control it. So this is for the general P norm.
But there are three quantities in the right-hand side. So from which of these three things this omega g does not depend on D at all.
Yes.
But so the right one, right?
This one is one thing. And also this B of P, the way you actually prove it is that you actually choose a suitable Schatten P norm. If you choose the Pth norm to be something like log of the dimension, then you can actually control the operator norm.
Oh, okay.
This Schatten.
I see.
So that's where this comes from. But this B sub P, this also kind of depends on your graph. And for the free graph, this edgeless case, this will actually be of the constant order. So in the free case, you don't really see any dimension dependent. So you just get a constant.
Okay, thanks.
Any other question?
Maybe I can.
Yeah.
Is there any universality in terms of the semicircular laws? Can they be generalized to other free variables, freely dependent variables?
This result?
Yeah.
So this result we can prove for a lot of different things. So for example, another thing that people care about is that these you can replace by the left regular representation of right angle Artin groups. So you can more generally consider if you take any basically groups, you can consider the graph product of these groups, and these objects you can replace by their left regular representations and so on. You will get this same result.
The question? So then let's thank Raghavendra again.